Okay, so we're going to try an application of exponential functions, finding maxes and mins. So just a quick little review. I've got our exponential function here. And what we're going to do is find the derivative, determine if the function's increasing or decrease, and then find any points of inflection or intervals of concavity. And obviously looking at our function here, we're not going to have any max and mins or points of inflection. We have one thing of concavity. And we already know it's increasing because it's our exponential function. And our e is greater than 1. So let's just go through the steps. So the derivative, so we know the derivative of e to the x is e to the x. And so what this means is that if you were to plug in 1, the slope is 1. You plug in x, the slope is e to the x. Whatever number you plug in, that is the slope of the tangent. So if we were to plug in 2, you would get e to the 2, and the slope of our tangent would be e to the 2. So it's the y value. That's it. So is the function increasing or decreasing? Well, we know e to the x is greater than 0, which means it's positive. So it is increasing. And we know that also by looking at its picture. Now let's find its second derivative. Well, what is the second derivative of e to the x? It's e to the x. So the same basic idea. This will never equal 0, so it's not going to ever have a point of inflection. But what we do have is that e to the x is greater than 0, which means it's positive, so it's concave up, which matches what it is. Our graph looks like this, which means we are concave up. So we can use these exact same rules for any application to determine if it's increasing or decreasing. Remember, if the derivative is positive, then we know it's increasing. If the second derivative is positive, we know it's concave up. If the first derivative was negative, it'd be decreasing. And if the second derivative was negative, we know it's concave down. All right, so let's try our application. I figured I'd pick one that is relevant. So after the consumption of an alcoholic beverage, the concentration of alcohol in the bloodstream surges as the alcohol is absorbed. This is your blood alcohol content. Followed by a gradual decline as the alcohol is metabolized. The function here models the average BAC measured in milligrams per milliliter of a group of 8 male subjects T hours after rapid consumption of 15 milliliters of ethanol, approximately 1 alcoholic drink. So they took this drink. This is now their blood alcohol content. Okay, so find the max blood alcohol content of this function, and when does it occur? So after consuming this alcohol, when do they hit the max? And so we're going to do our basic steps, which is to find our derivative. So we take our function c of t equals 1.35 t e to the negative 2.802 t. And I had to add a t there because I forgot it. Oh, and then we split it. So we know that it's being multiplied, so this is product rule. So the two different t's that we have, we can multiply. So this is 1.35, and then this is our exponential, so e to the negative 2.802t times the derivative of the top. You don't have to write that. We already know it's negative 2.8. So it's negative 2.802 e to the negative 2.802t. And then we do our little cross multiply. So 1.35, and again we just rewrite, plus, and then it's this one times this one. So negative 2.802 times 1.35t. All right, that multiplied is negative 3.7827. So we're going to change that to a negative 3.7. I already forgot it. 827. All right, so that was just the coefficients, and then we have a t, and then we have our e. Now I'm going to hit pause here and move some stuff, and then our e. And just like we did with the previous derivatives, that e is just going to transfer down, so it's always going to be there for us to factor out. So we factor that out, negative 2.802t. Put our parentheses, 1.35 minus 3.7827t. And then this is our derivative, so it'll tell if it's increasing, decreasing, and whatever. But we need to know when does it equal 0. So you know that our exponential is never going to be 0. So this is the main reason we factor it out, is we can see what this nice little function is here that will give us our max. So we set that equal to 0 and we solve it. So our t equals 0.356, and we'll just say 9. And t is in hours. So once we have all this stuff, we want to write everything down. So our t here is the number of hours, and our c is the amount of BAC in milligrams per milliliters, and it's our BAC. So we know what everything represents. So we already know that our c prime of t, this is dc dt. So this would be milligrams per milliliter per hour. So it's the rate of change in milligrams per milliliter per hour. And then that makes this hours. So we can convert it now to minutes if we want, but we're going to leave it in hours. Okay, so what we need to find now is the max. So if we take this t, plug it back into our c, we get our answer. But we're going to do this all in a nice clean step to make sure everything comes out perfect. So we already know that this is 0.3569. Has to start at 0. And so now if we take our c prime and we plug in a number in between there, so like 0.25, that should come out to either positive or negative. And then something past it, like 1, should come out to positive or negative. And we're plugging it in to our derivative. Now, this is always positive. It's greater than 0. We already know it has that decrease like that. So it's going down because it's got that negative exponent. It's just this one that we have to worry about. So if I take and plug that in the calculator, it'll tell me positive or negative. So plugging in the 0.25 into that part, it comes out to be positive, which means our function's increasing. And the other one we don't even have to do. It's a 1. So that's going to become 3.7, and 1 take away 3 is negative. So we know it's decreasing from there on out. So intervals of increase, that's what it asks for, would be from 0 to 0.3569, and you can use parentheses on both if you want. Interval of decrease then would be from 0.3569 to infinity, well, to whenever it completely removes itself from the body. All right, so now if we plug this in the calculator, the function itself, it's going to verify everything. So 1.35 x second e, the negative 2.802 x. Now, this is our x and this is our x, and we want to change our window first to 0. So make sure it says 0, 10. Once you have those put in, and I just put 10 as a random number, you can put 15 or 16, hit zoom 0. That will then fit our graph. And there we have it. So now our max should be right there. So if we go second calc, maximum number 4, we know a left bound would be 0 because that was our window, and a right bound would be 10 because that's our window. And we enter and it says 0.3569. That's exactly what we got. And then what it also tells us now is our max BAC. So it's 0.177. So our max is 0.177 milligrams per milliliter. And our time that it occurred was 0.3569 hours. And our interval of increase would be then from 0 to 0.3569, and decrease would be 0.3569, comma, infinity. Now, obviously, it's not quite infinity, but the way our function works is it's going to approach really, really close to eventually 0. So then we just say it's 0. But you can see everything matches. It's increasing to that point and decreasing from that point. So everything works well. So if they ask for the max or the min, it's the same thing as before. You take the derivative, set it equal to 0. The way it works is you always want to factor out that e because it's not going to be a part of the problem. These are going to be above 0 and sometimes less than 0, but they're not going to be 0. So we want that one right there, the thing that doesn't have the exponential function in it. Set it equal to 0, solve, and there's your answer.